Good morning everyone. Today we see about the design of cantilever slab. Myself Dr. J. Savayaruban, Professor and Head, Department of Civil Engineering, Rohini College of Engineering and Technology. The cantilever slabs are common feature in building due to the need having a bigger space at the upper floor. To achieve this, architect normally extend the slab beyond the ground floor building line, thereby forming a cantilever. So this diagram shows that a cantilever projection of the given slab. So here one end is fixed, other end is free, like this is a cantilever slab. So we have to see one problem regarding a cantilever slab, how to design the cantilever slab and how to do the reinforcement detail for the cantilever slab. So design a cantilever Kaja slab projecting 1 meter from the support using M20 grade concrete and Fe 415 HY SD bars. Adapt a live load of 3 kN per meter square. So length of the member is given as 1 meter and the load, there is a live load is given 3 kN per meter square. Then the characteristic compressive strength of concrete is given as 20 Newton per mm square and the yield strength of steel is given as 415 Newton per mm square. So based on that we have to find out the tau BD value. So the tau BD value is 1.2 Newton per mm square for plain bars M20 grade concrete. So first we have to find out the depth of the slab. So the effective depth we have to find out D is equal to span by 7. So this is getting from the IS 456 2000. For a cantilever slab we have to find out the effective depth. D is equal to span divided by 7. So the span length is given by 1 meter, that is 1000 divided by 7, that will be equal to 142.8 mm. So we have to adapt the effective depth as 150 mm. Normally we have to provide 20-25 mm cover. So overall depth of the given slab is 175 mm. So adapt 150 mm at the support. There is a minimum depth at the support. Gradually it will reduce 100 mm at the free end. So we have to find out the depth and provide, like in the support we have to provide 150 mm. That will be gradually reducing to 100 mm at the free end. Next we have to calculate the loads. The self weight of the slab normally we have to calculate by, so that average value in the fixed end we have the depth of 150 mm, in the end we have the value of 100 mm. So 0.15 plus 0.10 divided by 2, this is the average, into unit weight of RCC, this is 25. So we will get 3.125 kilonewton per meter. The live load is given in the problem 3 kilonewton per meter. The floor finishes we have to take in as 0.875 kilonewton per meter. So total working load will be equal to 7 kilonewton per meter. So we have to find out the design ultimate load. So WU is equal to 1.5 into 7, that is the total working load. We will get a value of overall load on the slab is 10.5 kilonewton meter. So ultimate load calculated. So based on the ultimate load we have to find out the ultimate moment as well as the shear force. Since this is a cantilever slab, the bending moment will be WL square by 2. So MU is equal to 0.5 into WL square. So 0.5 into 10.5 into 1 square, that will be equal to 5.25. Like we have to find out the shear force, VU is equal to W into L, that is WUL into L. So that will be equal to 10.5 into 1. So equal to 10.5 kilonewton. Next we check the depth. Already the depth is provided. We check the depth. That depth is enough to carry that moment. For that first we have to find out the limiting moment. That is MU limit is equal to 0.138 FCK into BD square. Substitute all the values here and finally we will get a value of 62.1 kilonewton meter. Already we find that maximum moment, that is MU. MU, that value is less than MU limit. So the section is an under reinforced section. So we have to design the section is a under reinforced one. Okay, since this is a under reinforced section, we have to find out the area of steel reinforcement by using this equation, that is mu is equal to 0.87 Fy AST into D into 1 minus Fy AST divided by Fck into B into D. So substitute all the values here and finally we will get the AST value. So mu is 5.25 into 10 power 6 equal to 0.87 into 415 into AST into D is 150 into 1 minus AST Fy divided by Fck into B is a 1 meter width into D is 150. So finally we get the value of 105 mm square. So that the distribution rod normally we have to provide 0.12 percentage of B into D. So provide a 10 mm diameter bar at a 300 mm center to center. So that AST for a 10 mm diameter bar, our AST value is equal to 262 mm square. So in the direction, in the span direction as well as that is a main direction as well as a distribution, we have to provide 10 mm at 300 mm center to center. Next we have to find out the anchorage length. Already we know what is anchorage length. LD is equal to 0.87 Fy into pi divided by 4 tau BD. So we know the value of all the data, that is Fy 415, pi is 10, that is a reinforcement diameter of the rod is 10 mm, 4 into tau BD, that is 1.2 into 1.6. Finally we will get a value of 470 mm. So this is a mild steel reinforcement, so we have to take a 60% value. So finally that anchorage length will be 470 mm. Finally we have to find the deflection check. So for that L by D value we have to find out. It is get it from the codal provision L by D basic into modification factor KT. So for that first we have to find out the percentage of steel reinforcement, that is 100 AST by BD. So 100 AST 262 divided by 1000 into 150, 0.174 mm. That's the percentage of steel we have to provide at 0.174 mm. So the KT value, that is a modification factor, we have to get it from that IS 456 2000. The graph will get 1.8. So that L by D maximum is equal to that, we know the L by D basic value is 7. So 7 into 1.8, that will be is equal to 12.6. So actual L by D value is 1000 divided by 150, that is 6.66. So the value is less than L by D maximum. So hence the slab satisfied the deflection criteria. So this is figure shows that reinforcement detail. So the 10 mm diameter rod at 300 mm center to center. In the end portion that slab is reduced to 100. Here that slab having the value of 150 mm. The anchorage length is already we provided 470. Here the 270 remaining 200 mm. This is all about the design of cantilever slab section. Thank you.